on page 62. Interstellar reddening. This is the actual reddening of visible light. And I hasten to add, this is not redshift. That's something else. We'll get to that down the road, okay? All right, it's caused by a scattering of visible light by interstellar dust. Okay, shorter wavelengths. Shorter wavelengths, and that would be violet, blue, green, scatter more. Longer wavelengths. And they punch through. Think of a red sunset. This is what's going on. I think we've all had the experience, especially on a hot, humid August evening. The sun gets down on the horizon, and so it's got a lot of atmosphere to go through, and there's a lot of dust and moisture in the air. And sometimes you can look right directly at that sun, and it's this beautiful red. Well, that's because all the other wavelengths from the sun have been scattered by that, that thick atmosphere. So that's what's going on here. That's what interstellar reddening is about. It's the same as a red sunset in essence. Okay. Supernova remnants. That's out there. Supernova remnants are, we're talking about an expanding shell of gas at high speed. Now, this shell of gas when we talk high speed, we're talking about, in some cases, even a relativistic velocity. So that's a lot of kinetic energy. That's a tremendous amount of kinetic energy. Remember, When we talk about kinetic energy, that's the energy of a moving object, okay? So, impact with surrounding interstellar medium Okay, so this expanding shell of gas at a tremendous high speed slams into surrounding interstellar medium, and this gets this is where we get into excitation of electrons. We've talked about those electrons jump out into the high speed lane, okay, and then as they drop back down, they emit photons. So that's what we're talking about here. All right. Also, all right, these impacts with the giant molecular cloud can stimulate star formation. Why? Because at that point it has sufficient kinetic energy. And this shell of gas contains heavier elements. All right, so what is the process? How does this whole process unfold? All right, so we'll walk this through. This has to do with gravitational collapse. This is why we say gravity is king. We start with something called Bach globules. Very small, dark nebula. Very small dark nebula, they are condensed within a giant molecular cloud. Within those Bach globules, number 2, we have dense cores. They are compact regions of gas and dust. within Bach globules. So a way to think about this is to think lumpy gravy. That's what we've got going on here. We have interstellar lumpy gravy happening here. Now, this is where it starts to get a little bit weird. The core temp must be cool enough to allow collapse. What happens is higher temps will overcome gravity. And prevent collapse. What happens if the temperature is too high, the particles reach escape velocity. This gets us to something called the Jeans instability, named after the astronomer Jeans. The Jeans instability is 10 kelvins. That's 10 degrees Celsius above absolute zero. Absolute zero. That's roughly 273 degrees Celsius below freezing. That's somewhere, I think, around 460 degrees below zero Fahrenheit. So, yeah, that's pretty cold. All right. This is the temp at which gravity overcomes temp. And therefore allowing collapse. Less than escape velocity. All right. I want to pause and explain a little bit more about this, just kind of flesh this idea out. Remember, this is where it's helpful to have certain definitions ready to go. Remember that when we talk about temperature, what we're talking about is the average kinetic energy of the particles in a sample of material. Recall that atoms and molecules move faster the hotter they are. You know, we learned that back in 6th grade. and that is true. Absolute zero, the rough street fighting definition of absolute zero is that temperature at which all atomic and molecular motion ceases. All right. So we're talking about just a mere 10 degrees above absolute zero, at which point gravity can overcome the motion of the molecules and atoms in play here. Remember also that in order to have gravity or gravitational attraction, you've got to have mass. And we define mass as a quantity of material, a measure of inertia, or just plain stuff. Okay, so this is what we're talking about here. We're talking about atoms and molecules getting almost to the point of absolute zero so that their motion is right down to nil. Only at that point are they sitting still, moving slowly enough so that the gravity that comes from their having mass is allowed to take over and start pulling them together. The gene's instability. This is the critical piece right here, is the gene's instability. Okay. A couple other terms here. Accretion. Accretion is a process of increasing or accumulating mass in a central region. It is gravity driven from the inside out. Think of water going down the drain, kind of like that. All right. A protostar. What is a protostar? It's a newly formed object, not a star yet, in the center of accreting mass. Okay. Most heat at this point is caused by infalling gases Okay, most heat is caused by the infalling gases colliding with the surface of the protostar. It's sort of like hammering a nail. If you've ever hammered a nail and you ever noticed that the head of the hammer or the head of the nail got hot, some of that was from friction, that's true, but most of it was just from the impact of the hammer that causes that heat. So yeah, that can do that, and does. Okay. At this point, the radiation is primarily infrared. That's below the frequency of visible light. All right. Now, if this protostar is not spinning, it collapses to a single sphere. And it becomes a single star. But if it is spinning, which is the majority of cases, then it collapses to a disk. And then it condenses to one of two things. It condenses to 2 or 3 stars, or if lower mass, a single star with planets. And that's us. That's how we got here. Now, there are rare cases where you may have a double star with planets, but that is by far the exception to the rule. Generally speaking, if it has sufficient mass, it'll collapse to a disk and then to 2 or 3 stars. Or if it's a lower mass protostar, it will collapse to a single star with planets. And that's generally how that goes. So, all right, we'll pause here.